guys, we're the Aquatic Sensors team. Our job is monitoring an artificial aquatic ecosystem. I'm Zach Bunn. I teach pre-AP physics and AP environmental science at MEDSA. My degree is marine science with biology and genetics as a kicker. So, kind of an odd pathway, but I'm really kind of enjoying this project because it plays into a lot of the stuff that I have enjoyed studying in the past.
I also teach at MEDSA. I've been teaching now, this would be my 6th year. I teach AP Bio, Biotech Engineering. Yes, I'm doing this because he caught me off guard. And AP Biology, have 2 kids, a 4-year-old and a 9-month-old. And I've also very much enjoyed doing this project.
Lori Wolf, I teach at Nago Middle School and life science, and I have a biology major also. And so I'm looking at it to see how it influence the little kid, the smaller ones. And I enjoy this. I was telling them that I think I'm the only teacher in my school that has fish tanks in their room. So anyway, even out of all the science teachers, I'm the only one that has living stuff in my room. So anyway.
All right, so our purpose here, the project that we're working on, is actually designing a wireless sensor network so we can monitor several factors in the artificial stream complex that we all toured the first, Wednesday? So general idea, what we're looking for is a way to use telemetry to monitor temperature, pH, and dissolved oxygen, so that Luke doesn't have to drive out there every time he wants to take a leak. Simple enough, right? So what we're doing, you guys can read this, it's pretty much what I just said, restated, but this is our hypothesis that we're using for the research paper that we're writing. Problem statement here, we're going to build off of that. We expect to retrieve live data with a 1 to 5% error. We were watching our pH sensor go all over the place and we were thinking that might be a pipe dream. We'll talk a little bit more about that in a bit, but it seems that we're at least on the right trail for fixing that. Using our monitoring setup installed in our aquatic system based on controlled environment tests. So what that really means is we're building this thing here. We've tried testing it in an aquarium to kind of see what's going on. We're also building a tabletop model of what they have out in the field so that we can test it on that before we drag it out there and drop it in the water and see what happens. Through the process of that, we're trying to grind down the error and keep it within reason so this data is actually usable. Easy enough? Okay, here's some of the equipment that we're working with. When you start out, the first thing we really built is right over there. It's based on an Arduino, and this one doesn't have it, but when we take it out in the field, we're going to stack an XP on top of it. That's how we're going to wirelessly transmit. Okay, so what you're seeing on that top right picture is just the Arduino and the pH sensor mounted on there. The pH stamp is right there. You can see it's about the size of a penny. So a little bitty circuit, no way I could hand solder that, but don't have to. It comes in a little kit, you just plug it into a breadboard or into a shield, take off, you're ready to go. When we put the thing together, that's what it looks like when we're trying to calibrate this thing, doing a quick test. Worked beautifully in that aspect. And just to make sure that we had everything working properly and we're getting readings that were realistic, we had a spark probe that we also tested everything with to make sure we were getting similar readings across the board. And again, when it was just the pH probe, everything was syncing up really nicely. So the platform we chose for this was the Arduino, and the reason we did that is, there's actually several of them. First off, it's really cheap. An Arduino Uno microprocessor is about $35. The XP Shield stack on top of it, you're looking at about another $35. So you've now got a complete microprocessor suite with a radio transmitter. You're only in 70 bucks. That's not bad. Okay, so that's the first reason that we chose that platform. The second reason that we chose that platform is that it is a very popular hacker mod. So when you go online, you can get a tremendous amount of things that are already prepared. There's huge libraries of code out there. There's a bunch of already made code. Most of the stuff we used, we went out, searched, found something that was close to what we wanted and we knew compiled, and then tweaked it to fit what we wanted. Why reinvent the wheel when a lot of this stuff already sort of exists and you just need to tweak it for your specific model? And that's really the strength of Arduino, is there's so many people around the world working on it that you're almost certain to find somebody else who's got code you can use. The XP that we used is a pretty powerful little radio. Again, it's about the size, a quarter-ish. And indoors, it'll transmit about 40 meters. They say outdoors, you're looking at 150 to 200. I don't buy it. I think you're gonna get lucky to get about 120. But that's more than enough for what we're doing. Okay. It uses the Zigbee protocol, which is a pretty robust radio transmission protocol that allows for ad hoc node-to-node connection. In other words, if we go out there and we build 3 sensors and we install them and we fire up the network, those 3 sensor nodes should be able to talk to our data sync, no problem. Now if they bring more tanks online and they want to add 3 more, you don't have to reboot, you don't have to build new code. All you do is prep those nodes to work, turn them on, and the sensors will find each other. And they'll jump on the data net and just keep dropping data. Okay, so that's the big reason to go with an XP. And it's cheap. And it's pretty easy to work with. And again, you've got the same thing since it's meant to work with an Arduino, the code exists. Alright, so the last step is actually bringing it all together and bringing probes into this process. There's a million probes out there. There's a bunch of different ones you could go with. One company called Atlas Scientific actually makes probes that are designed to work with Arduino. And it just so happens that they make all the probes we wanted to use. So it made sense to us to go ahead and get the probes from the same place. That way they're using the same underlying logic and it just makes the programming easier because all of their system calls are similar, right? So once you learn one, the others aren't really a mystery. You just need to make sure you've got the same concept for the underlying logic. Coding is simple. Make sense? Everybody's with me so far? Excellent. So, this is what the Arduino looks like with the XP shield on it. So the microprocessor is actually that bit on the bottom. It's also got several other things mounted on there to help make this thing ready to work out of the box. This big card on the top is called a shield. It lets you do plug and play things when you want to add on different utilities to an Arduino. And it's this little stamp up here is the actual radio transmitter. That's the XP. You can't really see it, but this is the code, and that's the actual functioning program for the pH sensor. There's an up close one. This is actually where we wired in the thermistor. And here's one that Dr. Fu built, and then here's my mimic copy of it. That's what we're actually make work. So he came in and was like, here you go, make one of these. And I said, what is it? Oh, as he walked off. He came back later that afternoon and goes, how's it going? And I go, I think this is it. He goes, let's turn it on. So it's kind of been a lot of fun because anytime we've hit a wall, they've been there to help us. And they've always gave us a kickstart for, here's kind of the idea I want you to follow. And then they just let us do it ourselves. It's awesome. There's been no sit and get here. It's actually a good model for the way we try to teach our kids. And I think that's part of the reason I dig it.
All right, so as far as the tabletop, you've heard Zach's part. Zach took care of a lot of the XP Arduino. He came in with some background with that. It's kind of what you get with our kids. When you mix them up, some kids are going to be proficient in something, and some kids are going to be weak. So we've definitely learned a lot from Zach here. As far as the tabletop, we try to make this as cost efficient as possible, as well as something that is accessible for the kids to build. So we did incorporate last year's model over the aquaponics system, and we used that kind of a system to make our artificial stream system. Stream is the key word there. We're actually trying to create a string with it. In a little bit, we'll take you back there so that you can take a look at our prototype. And that is a prototype, by the way, so we're still working on it, like literally working on it. Right, so our constraints again were the size of the classroom. If you're gonna launch this into a classroom, you need to think about the size of your class. You also need to think about the size of your groups. So we're thinking anywhere between 2 to 4 of these built, about 2 feet apart. Or every tank's about 2 feet apart. Should be pretty sufficient, given the size of your classroom. And again, we also want it to be friendly enough for the kids to build. I think when you take a look at it, it's pretty constrained and it's fitted and it's not going to move. That's not what we want inside of our classrooms. We want to be able to have the kids collapse it and then take it with them or do something with it. So what you see here, it's a pretty constrained model, but that's not going to be the case.
Or
Just have to
be able
see
to
that.
collapse it and maybe keep the parts for next year when we do it again, or,
Right,
Like a Lego.
yeah,
stupid.
something like that,
that would be awesome.
yeah.
And so the whole purpose for the stream here, or to simulate the stream graphical here, is to have it on an incline. So we decided that a 10-degree drop after every tank would allow for that stream. So we started at 3 inches, and then 2, and then 1, and then flat on the ground. And we will see that different species of fish are going to create their own niche. For now, we're just dealing with minnows. We have so many variables to play with, and that's kind of what Luke is faced with as well. I mean, the kids can pretty much create their own list of variables, limiting that to 1, so that they can test it. And again, we're testing for pH, DO levels, and the temperature of the water. So this is the, I know a lot of you guys have seen this one before. So he's got 24 tanks out there. They're about 6 feet in diameter. He's got these 3, that one, they're actually a closed system. And so that's on this little guy right there, I think is where we're gonna put our sensor cluster that's going to be embedded into the, we went ahead and ordered an otter box, and so it's water sealed as well as air sealed, and so that's where we're going to mount. That's what we're going to use to enclose our sensor cluster, and then to mount it onto the walls of the tank. There's Zach cleaning one of our small tanks, and then this is just a brainstorm here. And I'm somewhat proficient with 3D CAD modeling, as she has stated. It's one of the classes that I taught, and so I made a 3D CAD model of it. It's still a work in progress. And here are some sketches that we did. Here's the clamp there, and there's the box, there's the tank. And then we also thought of building 3 floaters. Again, we don't know what it's going to look like when we take it out to the field. So 3 floating devices here, each with its probe, so that we get a variable on site. Yixin is running into the problem where he's getting a recession frequency glitch on his pH with the temperature probe. So if distance will suffice to conquer the problem, that's what we're going to go with. But so these little guys right here are floaters, and these are our probes up here, and this is the actual attachment to the water tank.
Is this for the tabletop model or at the field?
This is the one at the field, right?
Like he said that we kind of each have our own deal that we are good at or better at, and so I think the 3 of us working together was really good. This is just the kind of our beginning lesson plan, investigating streams and water quality, lesson objectives. Student will design and build a river system. They will manipulate the flow of water in the system to study the biotic and abiotic factors that influence water quality. And then students will understand how environmental factors will affect the well-being of the river system. And then listed the TEKs that were involved. And materials needed, and we'll probably, we were pretty close. I think we were pretty close. That was our initial project deal, and then on down, we actually go through the objectives of the kit, or the actual experiment. And then there was the water testing part and engagement. I went out and found some videos on the watershed and water quality, middle school. This was a middle school level water quality thing. Student directed questions. How could you build a river system using plastic tubs and such, and just on down what supplies will I need, and then exploration. Students will explore, research river systems, you know, if you wanted to expand this out, they could actually do, you know, research before we started this on, you know, what does it take to, you know, what's involved when you test water quality and river systems, and then 2 higher level thinking questions and elaboration. They could develop a more sophisticated understanding through, like I said, researching river systems, designing and building the river system in the classroom, and then your technology there, or your terminology evaluation. You know, did they really get what we were wanting? And so, you know, their end product would be the evaluation. Did they actually get to do it?
That's high school or middle school?
They're gonna add some things to theirs as high school. We just kinda did a, you know, kind of a generic lesson plan. And then to, you know, since they do high school, I do middle school, you know, to kind of gear it towards each one of our courses. Literature review, we've each kind of pulled some articles. Zach pulled articles on the wireless sensor networks, and I read over some of those ones that he's pulled and actually did the literary review on so far. I think we've done like 4 literary reviews. Have you done? You've just been reading over them,
Yeah,
right?
I've just been reading and pulling more research.
And then after our seminar with Dr. Thompson the other day, and the big picture, these last few days I've been kind of concentrating on, you know, what is the state of our Earth? You know, because our big picture that we kind of came out with from her lecture was, you know, we only have one Earth. What are we gonna do? You know, and so I've been really these last few days pulling stuff. It's kind of depressing. You kind of get down. Because it was basically the literature saying we only got about 10 years to wake up, or else we're going to be in trouble. And so, so I pulled some articles about, you know, Earth and
Sustainability.
sustainability and you know, the climate change, not the greenhouse effect, but climate change. You know, what's really happening with that. So we are on our way to getting our paper done, and I think these guys have been working on the other aspects of the paper also. I've been kind of concentrating on the literary review, and they've been doing some abstracts and things like that, so.
Okay, so what we decided at the very beginning, we worked well. Me and Zach work at the same school, and then Laura just pretty much, you know, fit into anything that we were doing, is to divide the work and then to conquer. So that was our method in trying to complete all the tasks. And again, I mean, Zach came in with some already learned skills as far as the technology aspect on there. On the hardware side, we were making very good progress. Dr. Fu commented a whole bunch of times that we're moving at a very fast pace. And again, I think that's got a lot to do with what Zach already knew about the software. And so all the necessary equipment had been identified ahead of time. This was something that was trying to be deployed last year's meeting, but they got the materials, you know, very, very late. So I think they already knew what parts they were going to use, and it's similar to the problem that, you know, we're faced with this year, where they want us to create a video monitoring system on site. And so we've been doing a lot of brainstorming with that, but we already know what they expect for next year, so that we can get all the parts shipped to us this next year, so we don't have to wait for anything. The materials for the tabletop, they're under $30, so that's not too bad. And if the kids wanted to problem solve that, then they could pretty much try to create the tabletop using some of the resources that they had either at home or inside of the classroom. And that's kind of what I did, is I made a platform while I was waiting for Zach to come back from Lowe's with his cut sheet plywood. Zach wanted to do it that way, which is fine, but I made a very cost-efficient one with duct tape and some cardboard. So we all know that we can pretty much do anything with duct tape.
We just ran around here trying to find, oh, this is about 1 inch, this is about 2 inches. So
And it worked
we're
pretty good,
naked.
I'm just saying, like it worked. And then each one of us is going to create our own lesson. I teach 10th graders and 12th graders. Zach teaches 9th and 12th, and then she teaches 7th graders. So all of us have to walk out here with a lesson plan, and that's also in the development plans. We try to get something with Dr. Owen House, some sort of incorporating lesson plans, teachers, and then a possible trip to Brazil to further lengthen this.
Well, you want to go to Brazil, huh?
That would be awesome. That would go to Brazil.
When he started talking about it, we all like,
Yeah.
hey,
Part of the
here we are.
grant, isn't it?
That would be great.
Here we are.
Yeah, he's applying for a grant. All right, so here's a little bit more specifics on what we're working with. The sensor cluster has been created, but we haven't put it in that OtterBox enclosure yet. So it exists, it's mostly functional, we just haven't packaged it. The DO and temperature probes seem to work fine. Like there's no issue, they're giving readings that are reasonable and consistent. The pH probe, however, has been providing inaccurate data. Yixin has been in contact with Atlas a couple times trying to chase out that gremlin, and they have not been especially helpful because I'm not 100% sure they were understanding the question he was asking. But I think it's one of three possible things. We've pretty much got a solution for any of them depending on which one it ends up being. Communication between the sensor cluster and the data sync has been effective. We've got a clean front-end user interface that's built on LabVIEW. LabVIEW collects the data, drops it into an Access database. That Access database is linked to a website. So that data is pretty much flowing in a passive manner directly from the sensor clusters to the internet in an uninterrupted stream, which is where that tower comes in. Because if we get a nanolink out at the water research facility, then you can take readings from anywhere. Now, by the end of this 6-week period, we're hoping that it's not just a passive thing, but that you can also send commands to it. So if you want a specific reading at a specific time, like if you want to do a very specific temperature in there, that will alter the pH and the DO a little bit on how they read, because it will adjust for that. Now, back on this, when we talked about there's a little bit of problem, all of these probes work off of voltage. Okay, so the pH probe and the DO probe both pass voltage through a sensor, and that's how they're taking their reading. What happens when you put electricity in water? Okay, water's a current, it's going to interfere with each other. So there's two possibilities, really, for where the problem is. Either the problem is with the circuitry itself and pushing the voltage into the probes, and it's just not able to give it enough juice to make it read properly. So one of the things Yixin's been looking at is building a transformer to split the DC power, and we can flicker them that way. Another way would be to put it directly into the code, so that one probe is on, then the other probe is on, then one probe is on, and just back and forth that way, so there can't be interference that way. Now, another option might just be distance. You know, if we put one probe in one place and one probe in another, the current's only going to carry so far, and at some point it's going to have to stop interfering. But the problem with that when you're dealing with water is you can get microzones that are very specific in what's going on biochemically. So if we separate these probes too far and put them in different parts of the tank, are the readings really applicable to what we're trying to do? So distance might work. It's a last-ditch effort. We would rather control the voltage. But yeah, other than that, we've got the tabletop model that we're going to show you guys in a second as our demonstration. Joe's really taking point on that. Forgive us, it's messy right now. Like you said, it's a prototype. The end goal is going to be something that is replicable by the kids and cheap. So when you're looking at it, we scavenged a lot of parts. Joe's cardboard model was great. I didn't think about that. And then Yixin actually gave us an idea that we didn't think about. He's like, why are you guys raising it up? Why didn't you just cut a little bit deeper into the tubs? And we looked at him, and the real answer is we didn't think of that. But instead what I said was, well, these aren't very tall tubs. If we cut that far down, we won't have enough water in the last one for a sustainable ecosystem. He goes, oh, okay. And he walked away and I was like, whew, got away with that one. So, you guys ready for a field trip?
Well, I was thinking, perhaps we do questions.
Okay.
I was thinking, I don't know if this is okay with you all, if we do questions and then the other presentation, and then when we break for demos, we do the two teams.
That's perfect. Okay.
Because otherwise we'll have to go do the demo, then come back
Yeah,
here, and
so
then,
that's probably a good idea.
right?
Okay, so then we'll finish this out. This is just us working. This is actually what you're about to see, is the sensor clusters and the aquariums, and then the tabletop model. Yushin looking pensive because he's
Yeah.
not real sure if it's gonna
That's
work.
how I was looking the whole time.
Yeah.
It's like, how in the heck
It's a
am
little
I
bit of a
gonna
nail
finish
biter,
this?
guys. Also, we're about to fill tanks of water that we cut holes in inside the computer lab, so that's got us a little bit nervous.
With no
When I was walking by earlier and I had the cart and I had all these buckets of water and I'm walking backwards through an electrical engineering department, I'm thinking, this has gotta be these guys' worst nightmare. So
Yeah.
walking backwards with buckets of water, just not a good idea. Alright, so our next steps are really the data collection, wow, that's a tough word. Analysis and further improvement for the probe itself. Looking a little bit about the video monitoring for online users. That's what Joe mentioned with Dr. Hohenhaus. And then the final report is where we're going with this. Now, this one is really interesting. It's kind of an issue because an Arduino does not have the bandwidth to actually process live data. You could maybe get a grainy JPEG every 10 minutes, but streaming actual video, not gonna happen. Now, there's workarounds and there's things online that I found that might do it, but really, for what they're looking for, we're gonna need an entirely different, it's just a different core processor is the way it really works. We could maybe step up to an Arduino Mega or something like that, but I don't know. By the end of this, assuming we get our current project finished in a timely manner and working appropriately, one of our stretch goals is to start laying out a design for that video streaming and start making a parts list so that hopefully we're invited back next year and we can finish that out. Do you guys have anything you want to add?
It's good.
Cool.
Good, we're ready
So-
for questions.
Yeah, question time. Did you have the lights first?
I don't have a question, but I have a comment. I don't know what you can do with this water, but distance, some of these sensors can be used as relays. So when the signal attenuates, you can use the relay to do that.
Yeah. Pretty much the way we've been doing it instead is to keep the leads as short as possible and have them, right on top of the sensor node.
No, I think when he's talking about distance, it's not wireless, but the distance of the wires.
Yeah, the
are
probes
there
between
to-
each
The
other.
two probes being far apart, would give you different
being in
readings.
the same area of the wire.
Yeah,
That's-
within the tank. So yeah,
That's
the,
safe.
And I think
yeah, the
that's-
signal attenuation isn't so much of a problem because we're keeping the leads under 2 feet. And from tank to tank, we're going wireless. So as long as we're within the XB range, it should be fine. Now, I'm still a little bit nervous about the packet protocol. The XB's native one seems to be working fine, but if we scale it up beyond, say, about 20 clusters, I'm worried about data loss. So we'll see.
I have a question about video monitoring. Is the nano station going to be able to handle the video monitoring? No. So
I think we'll have to upgrade.
that's where we'll have to look at the big installation.
How much bandwidth does the network actually
I
have?
have no idea.
Maybe you can use a Dropbox kind of approach.
Possible.
We don't have, the problem is we don't have solid
It's
internet
not-
connection to the
Yeah.
field station, and this is one of the things we've been discussing, we're looking at $10,000 or whatever to be able to get a
Right.
decent,
Like-
dish out there, so.
Yeah, sending the raw data points in the table format, the network should be able to cope with no problem.
But not
For
really-
streaming video on more than one camera, you're really gonna have to have a broadband
The
connection.
nano station link, we have had running for almost 2 years now, from here to Isa, it's about a 3-mile thing. It's giving us a throughput of about, I wish something was here, but I think it's not even, it's like 1 Mbps. So it's not, to me, the video is,
Einstein.
it's the second, I think the first step is to get the data from the sensors.
Yeah.
And I'm sure the other
It
station
would
will
definitely
support
work
that.
for that. I mean,
Right.
there's not enough tanks out there to be a problem with that.
And then we will have to see whether there is a $1,000 investment that will have
Then
to
we
be
go
made
looking
by
for money.
UNT
Yeah,
or
we're
something.
looking for money, absolutely. When are your sensors gonna be ready, and you're gonna need the,
We are hoping to test, to have this built by today, have it running, have it testing by early next week, and then deploy it out in the field by late next week.
Assuming the OtterBox shows up.
Assuming the
maybe
OtterBox
next
gets
week,
here in
then by
time.
Thursday or Friday, we should have one
Right.
of these in the field. And then the next week, we're gonna build 5 more sensor nodes. And, 5 sensor nodes, 1 data sync. That's the goal by
Is Luke
middle
aware
of
of
the week
your
after next.
Yes.
schedule?
Yeah, he does, and we're actually going out in the field with them on Monday.
You're gonna,
We're
okay.
gonna
I'll
catch
talk
more
to you,
fish.
I'll find out when
Okay.
you're
Yeah,
out,
keep in
and I'll
touch.
meet y'all out there on Monday too.
As I said at the beginning, we may need kind of extra hands the day we're gonna.
Yeah,
Right, the
I
tower.
just need to figure out what we need to get it up in the air on Monday, and I'll meet with y'all, and then we'll plan a work day next week.
Did Hohen House get with you? He's got a tower already, sitting out there doing nothing.
That's our town.
Okay, and apparently he's got some money left in one of his budgets that he can't use for anything fun, he said, but for actual material projects, like if we need to sink a foundation or something.
I'll talk to him.
Yeah, get in touch with him.
Yeah, he did say he had some money that could only be used for stuff like that.
Construction on actual
Yeah,
material.
I know what money's talking about.
So, just throwing that out, because I kind of want that now. Anything else?
Yeah, I had a question whether in your lesson plans, the tabletop and the stream science questions, whether you are planning to take some of the electronics data collection, the Arduino and so forth,
I
to the
absolutely
classroom.
Yeah.
In my physics classes, I'm going to use this as my circuits unit and kind of walk them through how to do this.
And this is definitely a lesson for differentiation. We really get GT kids, gifted and talented kids who are, moving very, very fast, and the whole sensor cluster system would be awesome for them. To just
Instead
kind of
just-
explore and then try to do it. Like I teach seniors who can teach the sophomores how to build a sensor cluster.
And there may be situations where there's a group we just need to give a sensor cluster to and let them go, like with a Spark Pro. But then you get that one GT kid who is just super hands-on and great with electronics, and he's bored in your class. And you're like, well, tell you what, I built one of these, you probably can. Why don't you get started on it? And you can walk them through it. So it is a great
Oh, yeah.
differentiation tool. And then in my physics class, I'm just gonna make all of them do it. So some of them will fail miserably, and some of them will do great. And by the end of it, all of them will know something they didn't know at the beginning.
And they're not expensive either. So it's either we purchase them or
I already have a couple, just the
right,
frames.
$70. That's it.
Postage.
Nope.
So was the
But that
pH
good.
sensor the only one that was messing up?
Yeah. For some reason, the DO was fine. It was coming in within 1/100th of a point of what this spark was, but the pH was just all over the place.
Just jumping around?
Well, you'd plug it in and it would, the others were reading 7.5 to 8, and it would be reading 5.9. And then you'd unplug it, you'd plug it back in, and it would be 8.6. And you'd plug it in, you'd plug it back in, and it would be 6.3. Are you kidding me?
Gotcha.
So like once it picked a reading, it would stay on that till you reset it, but when you booted it back up, it was just gonna tell it what it was gonna go. We have a new one coming in, like we ordered another one from Atlas.
They had issues with that last year.
So, yeah, we thought of that too, we're gonna give that a go. But when we put them all too close together, it'll screw up the Spark Pro too, which is why I think it might be current.
Yeah. Are you running the filter at the same time, and the bubbler at the same time?
Yeah, we've been shutting off the bubble.
Okay, yeah.
Well, we've tried both
Oh,
actually.
we've done it both
Yeah,
ways?
I mean, he's tried to problem solve that for the past 2 days.
Yeah,
So
he's
it's like
been
building the
pretty deep
transformer.
in this.
Right.
Right now, he's moving wire for a transformer, so. Yeah.
Anything else, so let them go.
All right.
So next, I'm sorry, I missed schedule again, Dr. Wang here, or, did you get any response?
I can check.
One thing I forgot to mention, guys, is I